we're going to talk about what the first derivative, the application of the first derivative. That's really what that section. The first derivative can tell us where the function is increasing, where the function is decreasing, and if you're going to have a min or a max point, where they're going to be. If the derivative is greater than 0, that tells me the function is increasing. What does that mean, increasing? As you travel from left to right, what's happening to the y value for increasing? It's going higher. That's what increasing is, it's rising. If the derivative, first derivative, is less than 0, the function is what? Decreasing. So if the derivative is less than 0, that tells me your function is coming down, is decreasing. And if the derivative is 0, or where the derivative is 0, that's what we call possible. I didn't say definitely, possible min-max points. When I say min-max, I'm not talking about absolute. Could be absolute, could be local. But if you're going to have a min or a max, they're going to be where the derivative is 0. That's the application of the first derivative. Now, the problem with this, when we say increasing, watch this. This is an increasing function, right? This is also increasing. That's increasing. That's increasing. That's increasing. So the first derivative does not tell us how the function is increasing. It just says increasing. Then who's going to tell us how the function is going to increase? The second derivative. We'll get to that in section 4.4. So right now I'm not interested how is it rising. I'm just going to draw a line going up there. But when I get to section 4.4, I'm going to say, wait a minute. We can't just draw a line, straight line going upward. We need to know, is it increasing like this, increasing like this, increasing like this, which one of them? And that's where the second derivative comes in. So right now, let me just focus on finding where the derivative is 0, where the function is increasing, where the function is decreasing. That's all I care about for now. Make sense? So that's what section 4.3. We'll wait on the how till we get to 4.4. This is actually a nice picture of our book here. If f prime of x is greater than 0, the function f of x is increasing. If the derivative is less than 0, it's decreasing. And if the derivative is 0, then f is constant on a to b. They're not saying possible min-max. I like my definition because you'll see that in a minute. And you'll know if it's a min or a max. It could be actually a constant like this. Notice this one's a constant. What's the derivative here? 0. But it also could be a min point, because the derivative is the slope of the tangent line. I don't care about this. You're going to find out in calculus, you're not going to have these the sharp points like these. We do not like v's, because that means the derivative does not exist. So you're rarely going to see us graph something with the v in it unless it's an absolute value. It won't be there. So I don't like that definition as being constant, because in a few minutes I'm going to say, you know what, let's forget about that. Since we're not going to have undefined here, let's make it, and they'll probably do that down here. And how do you know, by the way, if the point, it's a min or a max? If you looked at this one, and you said, okay, well, I have a point. I know the function is increasing here up to a certain point, then it's decreasing. If you know it's increasing up to this point, then decreasing, can you tell what kind of a point is that? Is that a min or a max? That's a max point. But if it was decreasing first, then increasing second, what kind of a point is this? Min. That's how we know if we have a min or a max. We look at a function before that point, is it increasing or is it decreasing? If it's increasing before the point, then increasing after the point, it's not a min, it's not a max. But if it's increasing, then decreasing, that's a max. Decreasing, then increasing, that's a min. So let's take an example and see if we can find the min, the max, where the function is increasing, where the function is decreasing, all the good stuff. We'll start with a straightforward problem, nothing tricky about it. F of x equals x cubed minus 3/2 x squared. And I want to find where the function is increasing, where the function is decreasing, and is it, where you have min, max, all the good stuff. First step, if you're going to answer where the function is increasing, decreasing, so I'm looking to see where is it increasing, where is it decreasing, where is the min max. I want to find all the stuff. Since you hear the word increasing, decreasing, min max, your mind should immediately go to the first derivative. You're going to need that. The only way to answer that, beside using graphing calculator and cheating to see where the function is rising and falling, is by taking the first derivative. If you take the first derivative, that's what? 3x squared minus 3x. Let's set the derivative equal to 0. So 3x squared minus 3x equals to 0. Since there's no fraction, I don't have to worry about undefined here yet. So we just set it equal to 0. Factor 3x out. What do we have left? X minus 1. So there are two values, x equals to 0 and x equals to 1. These are my critical numbers. I'm going to be actually using boxes here for this section 3, 3, 3, 4, 4, 3, 4, 4, 4, 5, and 4, 6 to get you used to boxes, because the box will let you know if you forgot something or not. I'm going to jump to a new page. I'm going to leave a space on the bottom, and I'm going to make my box. The top half of the box for f prime of x, the bottom half of the box for the second derivative. In section 4.3, we're not doing the bottom half. We'll add that in a few minutes just to practice. This box, actually, this end is negative infinity, and that end is infinity. We're talking about this is x on the top. What the critical number is going to do for me, it says where the derivative is 0. We're going to take that box and break it down to 3 pieces. There's a cut at 0, and there's a cut at 1. That's where these numbers are, 0 and 1. So I have 3 segments. This segment from minus infinity to 0. This is from 0 to 1. This is from 1 to infinity. And while we add it, again, I'm laying the foundation for the next 4 sections all together. Somehow I'm putting them all together here. If I know the x value 0, can you find the y value? The y value, not the derivative, because that's the point. So let's see. When x is 0, what is the y value? 0 cubed minus 3/2, 0 squared, which is 0. Perfect. So when x is 0, y is 0. When x is 1, what's the y value? No, it's not the derivative. I'm not looking at the derivative. The derivative is inside the box. I'm outside the box. So that reminds you, like, do I test this one into the derivative, the second derivative, or the function? This bottom box is for the derivative. This is for the second derivative. I didn't even get to them yet. So I'm still outside the box, no derivative. When x is 1, that's 1 cubed minus what? 3/2 times 1 squared. What's 1 minus 3/2? Negative 1/2. One of the applications for derivative is you can graph a function. And I'm going to show you so far what I know. And we'll see if we can get an idea what the graph looks like. It says I have a point as 0, 0. That's right here. That's the 0, 0. I also have a point at 1 and negative 1/2. Somewhere here. I have a point there. X equals to 1, y is negative 1/2. But that's all I know. Now I need to know what's going on. Is the function increasing before this point, between this point and that point? Since you get 3 segments now, all during this segment right here, the function is going to behave the same way. It's either going to be increasing, decreasing, or flat. So we're going to take a test point to see if it's increasing or decreasing. What number should you use? You can pick any number between minus infinity and 0. So what do you want to use? Between minus infinity and 0, use numbers, reasonable numbers. So what should we use? Negative 1? 9 is too big, but negative 9 is fine. But make life easy on you because you're going to be plugging it into the derivative to see if that's positive or negative. So you want to pick small. In this case, you want to pick like minus 50, what's 50 squared and all this. Try to make it easy on yourself. But you can use any number. But that's the reason why I said reasonable numbers. So let's find the derivative at negative 9. Plug it into this one. 3 times negative 9 squared minus 3 times the negative 9. What's negative 9 when you square it?
81.
81 times 3? That's why I don't like the 81. Is that 243?
Yeah.
Plus 3 times 9, 27. I could care less what the answer is. Is the answer positive or negative?
Positive.
If it's positive, that's greater than 0. What does that mean? Increasing. Right? In this segment, the answer is positive. It is increasing, my graph. Between 0 and 1, what are you going to use? 0.5 maybe? You don't have a choice. Some number between 0 and 1 could be 0.5, 0.1, 0.1 will be good too if you want to. Anything. So let's see what the derivative at 0.1 or 0.5. I'm using 0.5. 0.5 when you square it, that's 0.25 times 3, 0.75. Minus 3 times 0.5, that's 1.5. Again, could care less if the number is what the number is. Do you think that number is positive or negative? Negative. That means less than 0. If the derivative is less than 0, what does that mean? Decreasing. Negative, that's decreasing. And let's pick a point after the 1. Again, reasonable number. Maybe we'll use a 2 here before George gives me 27. So I'll use a 2 there. What's the derivative at 2? Two squared is what? 4. 4 times 3, which is 12. Minus 6, positive or negative? Positive, that's greater than 0. Increasing. So now let's go back to 0, 0. Let's look and see what's going on. The function is going up, it hits that point, then it goes down. Is that a min or a max? That's a max point. A max point, that means if you were to graph it, will look like this. That's the highest value, right? This value, notice is decreasing. It hits that point, then what happens? It goes up there. That's what? Min point. So right here, the graph looks like this. So before that point, there's the 0, 0. Before that point, the function is increasing. That's what increasing is going up. What happens between this point and that point? Decrease. And what happens after that point? Increase. Now the only thing I probably did wrong is right here. Because I have a gut feeling if I graph it, the graph will look like this. I enlarge the picture just a little bit. It will look like instead of a straight line, will look like this. But we won't know that till we get to the second derivative. Then between this and that, it's probably going to concave and switch its mind like this. And it goes back up there. But right now, we can't show you that part because we don't know how to test it for it. When we fill the bottom half, that will tell us exactly how it's going to happen. But that's where the function is increasing. That's where the function is decreasing. That's where the derivative is, is 0, right? These points. We know where the min-max. Now, I could actually jump to 4, 4 and add that here just to show you that's what the graph and finish that table just to make it a practice. And maybe I'll do that. So I'm jumping to 4, 4. Well, I'll leave it because otherwise my video will be all messed up. So I'm leaving the bottom half to later. I can save these notes. When I come back to them, we'll grab them and reuse them again. Let's take another one. Now, let's take one where you might have derivative does not exist. F of x equals x squared minus 4 to the power of 2/3. Again, I want you to tell me where the function is increasing. Decreasing. And min-max. Now, to go back to the previous one, if you want to answer the question, where is the function increasing? Remember this one? Where is it increasing? From where to where? From negative infinity, we always give the x value. From minus infinity to 0. You don't include the equal sign. You go for increasing here. I don't have any room to write it. Increasing, I will go from x is greater than negative infinity and less than 0. No, it's not equal to 0. Or that's union set. When we use set notation, that's or union. Add to it from where to where? From 1 to infinity. X is greater than 1. X is less than infinity. Don't put the equal sign. They will mark it wrong if you put equal to 0. The 0, it's not increasing or decreasing. It's up to that point is increasing. From that point down is decreasing. Where is it decreasing? From 0, not including that point, to 1. So this is really the U symbol from set notation, union. The union of two sets, it's in either an A, or in B, or in both. So instead of saying or, we use union.
Is that how?
That's how probably the software is going to write it. Yep. I know my math lab writes it that way, and I don't know if WebAssign writes it that way or not. At other school, I teach Calculus 1. I use a different program, and it writes it that way. Let's take this problem here. Again, let's take the derivative. We're going to need it. What's the derivative? Again, we're reviewing for the test, basically. How do you take the derivative of this? That's the general power rule. 2/3 x squared minus 4 to what power? Negative 1/3. Are we done? Times 2x. The derivative, what's on the inside? F prime of x. 2 times 2x, that's 4x. 3 times the cube root of x squared minus 4. Let's find out where the derivative is 0. set for x equals to 0. That means x is 0. That's one number. And let's find out where the derivative is undefined. Take the bottom, set it equal to 0. The only way the bottom will equal to 0 if x squared minus 4 is equal to 0. That means x squared equals 4, x equals plus or minus 2. So how many numbers do we have for critical numbers? We have 1 here, and we have 2 here. 3 numbers altogether. I'm going to make a new sheet. I always do the box in a brand new sheet. As I said, I'm going to build it, leave it ready for later. The top half is the first derivative. The bottom half is the second derivative. The first derivative is 0 where? At 0. At x equals 0, we'll find what the y value shortly. The other one where? Negative 2. And 2. We'll prove that later. You'll see where it's undefined. Actually, it's going to run through down here too. But we'll prove that later. That when we take the second derivative and see where the second derivative is undefined, where the first derivative is undefined, the second one will also be undefined, the same points. But we'll prove that later, so I'm not worrying about this. That's just something down the road. And again, I'm outside the box. I need to find the y value for each one of these. Outside the box, that means go to my function, not the derivative. What is the value of x? The value of f when x is minus 2. What is f of minus 2? What's minus 2 when you square it? 4. 4 minus 4, 0. That's 0 to the power of 2/3, which is what? 0. So the y value here is 0. For the 2 is also 0. What's f of 2? 0 to the power of 2/3. 0. And the last one, what's f of 0? That's negative 4 to the power of 2/3. If you have a calculator, here we go. Parentheses, negative 4, close parentheses to the power. What'd you get there, George?
Negative 2.52.
Okay, you're going to put parentheses here. Let's see if that's where you got. So you want to make sure you tell 2/3 in parentheses. If you don't put them in parentheses, you're going to raise it to the power of 2, then divide the answer by 3. And I got an error. Why? Let me see if I typed it wrong. Oh, I probably didn't use the right minus sign. Is that the right minus 4? That should be okay. Maybe this calculator is just cheap calculator. It doesn't know what that is. Yep, this one is a cheap one. If I pull my good one, because that's 16, cube root of 16. 16 to the power of 1/3. Oh, parentheses. You get what you pay for with calculators. It's 2.52. Is that what you got?
Yeah.
Yep.
Oh,
So, if, yeah, negative. So it'd be negative. It won't be negative, no. It won't be negative. Would you use the calculator? Make sure you put the negative 4 in parentheses. Did you put the negative 4? Here we go. Get a good calculator.
Separate them.
Yep. Here we go. In parentheses, negative 4. Oh, my minus sign sticky. Negative 4 to the power, parentheses, 2/3. 2.52, positive.
Why does that not come out negative?
Because that means, when you look at it, it means the cube root of negative 4, and you're going to square it. That's what it means. So when you take the cube root of negative 4 is a negative number, you square it, that's a positive. Or it's actually the cube root of negative 4 squared on the inside first. Well, if you square it on the inside first, that's a 16. That's the cube root of 16. And that's what I did on my cheap calculator. I said that's 16 to the power of 1/3, because this doesn't do that number. So now we get the answer 2.53. But that's the reason why. Now we need to know where the function is increasing, decreasing, and all that. There's your derivative. Here's the good news. Well, not a good news here. I thought that was a squared. But let's see. Let's pick a test value less than a -2. What should we use? How about -3? You don't want to use fractions if you don't have to, or decimals. It makes the math a little bit more complicated. Let me write the derivative here so I don't have to keep going back and forth. Normally I save this as a separate page, but here's the derivative. When x is -3, notice how lazy I am. 4 times a -3, positive or negative?
Negative.
All I care about, negative or positive. I don't care about the number. I don't even have to waste my time on it. -3 squared is what? 9. 9 minus 4 is what? Positive or negative? Positive, right? The cube root of a positive number is what? Positive. Times 3, that's also a positive. What's a negative divided by a positive? Negative. That is decreasing. The derivative is negative, is decreasing. Let's take a test point between -1 and 0. How about a -2 and 0? How about a -1? You can see my subconscious knows what the number. I'm going to test the -1. If you want to put minuses there, just a reminder, like it's going to be a negative, just you can do that. Minus, 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 that's a negative value. Let's try the -1. Four times a -1, that's a negative on the top. But in the bottom is going to be a -3. The cube root of a negative number is negative. What's a negative over a negative? That's a positive. So in this section, that's a positive. That's what? Increasing. Between the 0 and the 2, use a 1 here. What's the derivative of 1? The top is positive. The bottom is negative. What's a positive over negative? Negative, that's decreasing. And more than a 2, I'll pick a 3. Again, some reasonable numbers. Don't go crazy with them. F prime of 3, that's positive on the top. Positive on the bottom. What's positive over positive? Positive, that's increasing. What's this point here? Min. What's this point here, the 0 and 2.53? Max. What's this point here? Min. So if I go to graph it right now, this is what I know. I get 3 points. -2 and 0. Right here. 1, 2, somewhere here. That's another point. and 2 and 0, right here. Before the minus 2, before I get to this point, it was what? Decreasing. How is it decreasing? I don't know, something like this. What happens from this point to that point? Increase. What happens between this point and that point? Decrease. And what happens after that point? Increase. I bet you if we graphed it will be close to that, except the graph will look a little bit different. If you look at that graphing calculator, the graph might look like this, straight line here, but here instead of having that V shape, it might look like this. We won't answer that till we fill the bottom half. But we got a rough idea what the graph looks like just from the first derivative. Derivative does not exist right here. You have a V shape. I know that's going to be a V here. That's why the derivative does not exist. Anytime the derivative does not exist, we have a V shape. So I have a V shape here, a V shape. This is not a V shape because the derivative here will find out to be 0. That's horizontal, you know, a maximum value. One more example on this, then we'll go to the next section. The 4, 2, and try to finish them. What I'm actually doing with the box here, I'm doing is actually 4, 6. 4, 6, they said, let's put everything in the box and try to combine them. So I'm trying to just get you ready for that 4, 6. So once we get this box complete in 4, 2, and 4, 4, 3, and 4, 4, oh, we jump to 4, 6. Leave these handy. I'm going to need them. One more example. F of x equals x to the 4th plus 1 over x squared. Again, we have a test on Monday, so you're going to be given a problem like this on Monday. I'm going to say take the derivative. What method would you use here? The quotient, you have a fraction, right? If you want to. You see you can use the product?
Yeah.
If you want to. I said if you want to. I don't want to use either one.
Take out x squared.
If you divide by x squared, what would you have? This is x 4th over x squared plus 1 over x squared, which is what? x2 plus x to what? Negative 2. What's the derivative now? 2x minus 2x to what power? Isn't that easier? Take the derivative that way? You could have used the quotient rule. There's nothing wrong with it. You're still going to clean that. That's 2x minus 2 over x cubed. And if you want to find the LCD, what's the LCD? X cubed. That's 2x to the 4th, yep, minus 2 over x cubed. Notice that's over 1. You got to find the LCD, which is x cubed. So you multiply the top and the bottom by x cubed to make it 2x to the 4th. Now, where's the derivative 0? Take the top, or minus 2, equals 0. Factor a 2 out. Right? So that means x to the 4th equals to 1. X will be positive or negative 1. What is 1 to the 4th power? 1. What's minus 1 to the 4th power? 1. So plus or minus. So there's two numbers here. These are your possible min-max. If you're going to have a min or a max, they're going to be there. Or where the derivative is undefined. Here's one little problem here. If you look at that problem, it says x cannot be what? The original problem. Cannot be 0. Where's the derivative undefined? When x equals to 0. But x can't be 0. So when you go to your box, it says I can't use the 0. Anyone knows there's a name for that 0? X equals, that was on test number 1. X equals to 0. There was a name for that. What is that called? Vertical asymptotes. Very good, George. So to make sure you remind yourself that x cannot be 0, I always take a thick line where I can't miss it, and I go 0. DNE does not exist. The function does not exist. That's vertical asymptote. It's not a min. It's not a point. The function has a hole in it there. And actually, when I graph it, I'm jumping here ahead to graphing. Again, to remind me that when I graph it, not to connect that point, I draw a thick line there just to remind me. Right there, the function does not exist. Meaning what? As you approach that line from this end or from that end, either going to go to plus infinity or minus infinity. That's where the function is going to go to. They're going to go all the way up to the sky or all the way down to the center of the earth. And we have no idea which way till we start graphing it. I have two numbers we found out, and they are what? Minus 1 and 1. When x is minus 1, what's the y value? Let's find the y value first. When x is minus 1, what's minus 1 to the 4th? 1 plus 1, that's 2 over what? 1, that's a 2. And this is also a 2. So f, not the derivative, f of minus 1 is equal to 2. F of 1 is equal to 2. So these are outside the box. Now let's go inside the first derivative. Let's take a test point. Let's pick a value. What are we going to use less than a minus 1? Good. Between minus 1 and 0, negative 0.5. Between 0 and 1, 0.5. Between 1 and infinity, 2. Let's find the derivative at minus 2. Derivative. Let's look at this. What is the derivative at minus 2? There's my derivative function. Look at the bottom first. That number is negative 2. When you cube it, is that positive or negative? Negative. What about the top? Minus 2 to the 4th power, that's what, 16? 32 minus, that's 30 over a negative number, which is what? How about a negative? Positive over negative, which is negative. That tells me the function is decreasing. After that, the negative 0.5. That bottom is negative again. 0.5, that's 1/16. 1/16 times 2, that's 1/8 here. Minus 2, that's a negative over negative, which is positive. That tells me it's increasing here. Decreasing, increasing. What do we know? That point is what? Min. Was decreasing, then increasing. Let's take the 0.5. F prime of 0.5. The bottom is positive. The top is negative. It's the same numbers here. Negative over positive, negative. What does that mean? Decreasing. What's this point here? Min or max? Neither. Why? It's whole, right? It's a gap there. That's why I made the big thick line to remind you. That point is not connected, so you got a hole in the graph, separation. So it's not a min, it's not a max. And after the 1, we'll take the 2. That's positive over positive, which is what? Positive, and that tells me it's increasing. So that point is a min.
Are we using those two theorems we learned yesterday on this?
No.
Oh.
Nope. So now, the points is minus 1 and 2. That's 1 point. We know it's a min point, so it's going to look like this. And the other point is what? 1 and 2. Oh, actually, a little bit pushed it to the right, huh? I counted wrong. There's the 1. 1 and 2. And minus 1. The other one is 1 and 2. Right here. Let's look at the first point. What's going on before you hit that point? Decreasing. What happens when you hit that point? Increase. Can't cross that line. The function is undefined. What about this one? Before you get to that point? Decreasing. What happens when you hit that point? Increase. And that's what the graph for that will look like. So where's the function increasing? Increasing from 2 to 0, greater than 2, less than 0. Add to it. From where? 1 to infinity. Decreasing from negative infinity to negative 1. Add to it from where to where? 0 to 1. Min points, we have 2 of them. Negative 1 comma 2, 1 comma 2. Max points, none. Yes?
Do you use this if the function was when it was coming from the left, it was always increasing, and from the right, it was always decreasing? Like there was a horizontal asymptote?
I'm not sure.
Instead of the U shape, it was just like a big swoosh up and then a big swoosh down.
Big swoosh up. Just one goes up.
Like what e to the x looks like
E to, let me. E to the x will look like this, the graph.
Yeah, but
Like this.
yeah, that same shape, but with a vertical asymptote.
Up here. Let's see, I have vertical asymptote here.
No, it was the same, like it was still a vertical asymptote. But
Oh, vertical asymptote here.
yeah, and then it went down like that, and then down like that.
It could look like this here. Like that.
Yeah, but how would you use this if it was always increasing?
If it was always increasing,
Like there's no min on that.
that's always increasing.
Yeah,
So it could be a problem like 1 over x squared maybe.
yeah.
I don't know if that's always increasing or not, but if you have 1 over x squared, x cannot be 0, right? That's your vertical asymptote. Now that's f of x. The derivative of that, remember that's x to the minus 2. That's minus 2x to the minus 3, which is minus 2 over x cubed. So there are no additional points to cut the graph. So let's take a look at that problem. I don't know if that's what you're looking for, because that's a quick one. I think that's what you're asking, but I'll
Yeah,
so 1 over x squared. Again, you can write that x to the minus 2. Quickly, we know x cannot be 0. The derivative of that, it's negative 2x to the minus 3, or negative 2 over x cubed. Still, x cannot be 0. Right? The derivative, x can't be 0, so that's where you're undefined. So when you look at your box there, when you build your box, might be able to fit it here. This is f prime of x, f double prime of x.
This is a
Different problem. New problem. So the only addition we're going to add to the box is right here. That's 0. That thick line, because that's x cannot be 0. That's a vertical asymptote. And 0 and d and e does not exist as 0. So we take a test point less than the 0, let's say minus 1. Take a test point more than the 0, it's like a 1. What is the derivative at minus 1? The top is always negative. When this number is negative, what's negative over negative? That's positive. That's increasing. The 1 actually is going to be decreasing. If I did 1 over x instead of 1 over x squared, that'll be what you're talking about there. The top is negative. The bottom is positive. That's a negative. And that's decreasing. I do not have a min or a max, because if you look at that problem, this is the vertical asymptote. It's increasing. Now, where does it start? You mentioned horizontal asymptote. My horizontal asymptote happens to be 0 here. We'll talk about that actually in section 4, 5. So the function starts from here. It's increasing. It's going to go like this. After that, the function is decreasing and is going to level at that, because the horizontal asymptote at y equals to 0. So the graph will look like this. So it's increasing from negative infinity to 0, decreasing from 0 to infinity, no min, no max. If I did 1 over x, it might look like what we did before, 1 on the bottom here, where it's always increasing. But you still have to write increasing from minus infinity to 0 and from 0 to infinity, because there's a hole between them. So now let's bring in the second derivative, section 4.4.